So yesterday we looked at average, or not yesterday, a couple of days ago, but we looked at average rate of change. And we talked about how in grade 9 you do average rate of change between 2 points that are on a line, where the whole line has the same average rate of change. But you don't have to do it that way. It could be 2 points on a curve and find the average rate of change, or it could be 2 points on a line, or it could be like that graph of the person driving where it's like lines, but it's not one straight line. There's like different things happening, right? And when you take the average rate of change between those 2 points, you don't know what happens in between. You just get the average, but that may be appropriate. That's fine. And this definition came up about a secant. So here we are. We can write it down. The secant. A secant is a line segment that passes through 2 points on a curve. So the slope of the secant would be the average rate of change between the 2 points where it crosses. Okay, so that, will look something like this. Sorry. That will look something like this. So there's a secant. Okay, so we've got a quadratic, and we've got a secant passing through it. And if I found the slope between these 2 points, you can see that they're nice points. We're not going to do that, but if we did, that'd be the average rate of change between those 2 points. It'd be the slope of the secant. Okay, what is a tangent? A tangent is a very important definition. I talked about this the other day. Aside from when you do triangle, trig, that kind of thing. Tangent is a line segment that touches a curve at a single point, okay? And so it looks something like this. If I drag this up, and watch what happens to those 2 points. Okay, so the average rate of change, I can still find the average rate of change between all these 2 points. Still find the average rate of change. Any 2 points, you can find the average rate of change. But when it touches it at a single point, okay, and I can, if you don't believe me, I could scroll in and trust me, it is a tangent. It's not touching in 2 points. So though at that exact point, those 2 points that are forming a secant touch at that blue point that was already there. So now it's a tangent. I can't find the average rate of change between a point and itself, right? You'd be subtracting y from itself. You get 0 over 0. That's not going to work, right? You can't do that. So how do we find the slope of a tangent? And what is really important is the slope of a tangent is an instantaneous rate of change at a single point. So at any point, imagine that quadratic, that curve, is the height of a ball that gets thrown over time or distance or something like that. And we did this kind of the other day. If you took 2 points on that curve, you could find the average change in height over time. And at one point it was positive because it went up, and at one point it was negative because it went down, and at one point it was 0 because the height hadn't changed, right? So I can find the average rate of change between any 2 points. But what if I wanted to find the exact rate of change at an exact moment? How fast, what's its speed, either vertical or horizontal or whatever it is you're asking, at that exact moment? Like the speed that your odometer or your speedometer, measures on your car at any particular point. I know that if I drive an hour and I drive 100 kilometers in that hour, my average speed is 100 kilometers per hour. But throughout that trip, I sped up and I slowed down and I did all these things. And the instantaneous rate of change is what the speedometer would read at any one of those points. And that is something that's very important in mathematics and in physics and that kind of thing. How do we calculate it? So that's what we're getting into. This is a huge, huge, huge idea. You may have heard of something called calculus. Some of you may have taken it already. There were 2 famous people, and it turns out maybe other people thousands of years prior, who had problems that they couldn't solve and had to invent a whole new mathematics to try to solve them, and that became calculus. And this is like we're getting our feet wet a tiny little bit in the beginnings of calculus here, finding these instantaneous rates of change. But we're not going to do it the calculus way. We don't do it the calculus way. We do it a bit of a different way, but it's really important, especially if you plan on taking calculus. This is big stuff. Okay? So blah, blah, blah. We've already covered that. How do we do it? Today, all we're doing is estimating. We're not even calculating. Everything we do today are estimation techniques. There's 2 things that are important about them. There's thinking and understanding that goes into this between the relationship of average rates of change and instantaneous rates of change. What's the relationship between those two? And when we learn how to calculate it, something that we're going to do today helps our understanding of why that works, I think, which we're going to do that on Tuesday. So there's understanding that happens here, but this is an estimation technique. The other important thing is it'll be on the test, so you need to know how to do it. But like it's messy. It's not like fun mathy stuff. It's like kind of messy and it's long and it's not, it's still just an estimation and all the numbers still kind of work out nicely for us because this is a math class. But so heads up, this isn't like a super thing we do a lot of in this course, but it is a technique that has some real important understanding behind it. Okay, so here's what we're gonna do. In a pinch, you have some curve. For now, we're just working with quadratics, like for these couple of examples. So imagine you have a quadratic and you are finding the slope of the tangent, so the instantaneous rate of change. Remember, a tangent doesn't have 2 points, so you can find the average rate of change between, remember. So we're finding the slope of the tangent at some point P. You pick the point, I pick the point, whatever it is. Okay, how do we do that? We're going to pick a point Q on the curve that's close to P in some kind of meaningful way. We're going to find the average rate of change between P and Q, which we know how to do, that's easy. And then we're going to repeat this process to get a sense of what the instantaneous rate of change is like. So you got to do a whole bunch of these things, and then it gives you a sense. If you do it, you pick the right values and do it the right way, you get a nice answer. And especially when it's quadratics, it works out really nice. Okay, but it doesn't always work out that nicely. Okay, and there's sort of two main techniques that the textbook uses. It calls them something, it has a name for them, so we'll talk about that just so that you understand what it means. These are just like, I can imagine other textbooks wouldn't call it that. Like, this isn't a formal thing, but we're interesting estimation techniques, so that's what we're going to do. Okay, so estimate the slope of the tangent line to this curve at this point. So the first thing we're going to do, we're given that point. Sometimes you might be given it, sometimes you might not. First thing we're going to do is we're going to find some points, like this is our Q. We're just going to figure out what these points are. And because this is a long, messy process, I'm not even going to show a lot of work here. I'm going to show the values, but I'm not going to substitute or anything. So I'm going to go a little bit before the X. I'll start at 0.5, and I should have my calculator out, and I'm going to figure out the Y's. You guys can do this too, because you'll be faster at it than I will anyway, probably. So you punch that in, 0.5 squared plus 1 gives you 1.25. So there's another ordered pair on this curve. Okay, I'm going to do F at 0.9. So what is that? Well, I've gotten a lot closer to the point that we're trying to find the instant, like very close, right? Like we're talking really close. Okay, and I punch that in, 0.9 squared plus 1 works out to 1.81. And I'm going to do one step even closer. Okay. So now we're really, 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 really close, within 100th of a unit. And I get 1.9801. You might want to check this math, just make sure it all works out. Everybody good so far? If you feel like, what are we doing? I have no idea why we're doing this. I don't understand. That's okay. It'll make more sense when the process is complete, I think. Okay, if we've done one whole one and then it still doesn't make sense, then we have a problem. Then you can ask. Okay, so F at 1 is 2. We already did that one. 1 squared plus 1 is 2. That's easy. Okay, and then we're going to continue this process of F at 2.01. So now where am I? I'm just past the point. 0.0201, I think. F at 2.1 is 2.21. And F at, sorry, why did I pick 2? 1. Those should be 1s. 1.1, that makes more sense. And then F at 1.5. So if you look carefully, all of these values are like symmetrical around the point that I'm looking for. I've got 2 that are 0.5 away, before and after. We're talking to the X's here, not the Y's. The Y's work out to whatever they work out to. I've got 2 that are 0.1 away and 2 that are 0.01 away. Does that make sense? We got that? So here is one technique. It's called the preceding, following interval technique. What a beautiful name. Chunky name for a chunky process. So what we're going to do is we're going to, for the preceding and following, we're always using the point that we're trying to find. Okay? So I'm gonna start with the interval from 0.5 to 1. Okay? And I'm finding, what am I doing? If you forgot, we did talk about this, but what are we even doing? Finding the average rate of change between those 2 points. Okay? So let's see. It's going to be, so I've already got all the values done. If you take a look, I've got the y value 2 and the x value 1.5. So the difference between the y's over the difference between the x's, right? There's all the data that I need. So I'm just going to go 2 minus 1.25 over 1 minus 0.5. And it works out to 1.5. That's the average rate of change. Sometimes we call it the IRoC, and then we call this the instantaneous rate of change is the IRoC, or the slope of the tangent, slope of the secant. So that's a slope of the secant. Everybody good? Okay, so then we're going to do one step closer. See how we're always using 1, like the point that we're looking for? And we're progressively moving the second point that we're using closer and closer and closer. We're going to do a visual of that after. So this one's 2 minus 1 point. Do this on your calculator, please. Like, I want you to see it on you. So have your calculator out. Do it on your calculator. Over 1 minus 0.9. So it's going to be 2 minus 1.81 divided by 0.1. It's a really messy process. If you can do even a little bit of the math in your head, it speeds it up a little bit. Otherwise, you're like doing brackets on top, brackets on the bottom. It's even slow to punch into your calculator. Ugh. So frustrating. Can you tell I'm not a fan of average rate of change, or the estimation technique for instantaneous rate of change? What does it work out to? You get exactly 1.9. Okay, you should. Good. And then the last one, we get even closer. Really, really close. So it's 2 minus, like if you're thinking in your head, I don't really know how he's getting these numbers. I think that's fair. So you got to ask. You can ask later if you want, and I'll show you more carefully. But like, I'm fine. They're points. These are ordered pairs, right? y2 minus y1 over x2 minus x1. So if I'm doing these, which is this one and this one, it's y2 minus y1 over x2 minus x1, right? That's all that we're doing here. Okay, so 2 minus 1.9801 over 1 minus 0.99. So again, that's 2 minus 1.9801 over 0.01. What does that work out to? Who's got it? 1.99. What's the slope approaching? What's it getting closer to? Roman? 2, right? Doesn't it look like it's getting closer and closer and closer to 2? You can kind of see it happening. These were preceding intervals. Preceding intervals. We're not done yet. That was like just under half the process. Justin? Yeah. What? Okay, so you tell me why that works. Like, will that always work for every function that you're ever given for everything?
I don't know.
Right. If you have no idea, then absolutely you can't do that. It's a great question. It's good for noticing that. No, that's not a thing that we do. No, definitely not. Yeah. If you can prove it algebraically, then we could talk. I'm thinking that it will work for some. It might even be that might work for all or most quadratics, but other functions it won't. I can pretty much guarantee that. So if you do like a cubic or something else, it won't. That won't. Right. So anyway, good question. No, that's a good question. Looking for patterns. We're in math class, so that's what you're supposed to do. It's very good. Okay, so let's, I'm going to do something a little bit different here. I'm going to start really close just to kind of keep things in order and work further away. Okay, so we're going to keep going here. So now we're going from 1 less than or equal to x less than or equal to 1.01. So now we're going after the point. Okay, and that is 2.0201 minus 2 over 1.01 minus 1. Okay, and let's get all these finished. So 1 minus 2. Somebody do one of those, somebody do another, somebody do another. You don't have to do all of them, but again, it pays to do one. Anybody do the first one? .01. Look at the symmetry. Isn't that lovely? Isn't that beautiful? Anybody do the second one? 2.1. And then the last one works out to 2.5. As you may have guessed, if you're noticing the patterns here, you may have guessed that would happen. So these are called following intervals because they all follow. Now here's the final step that you would have to show if you were using this process. Okay, the textbook doesn't always pick values that are as close. Like it might not pick 0.99 or 1.01. Like it might not pick those. So you won't get quite as nice a picture of the fact that it's really approaching 2. But that's why I like to use these numbers that are very close. Makes the decimal punching in a calculator a little bit messier, but I still like it. It's a good visual. Okay, but like I said, for quadratics, folks, it's really obvious. For other functions, which you will have to practice with a little bit, it's not so much. So it won't always be this pretty. So what we do is we can kind of see that it's approaching 2. We can kind of see that it's approaching 2. But if I take the average of those two, so I add them together and divide by 2, I get 2. I get an answer. So there's my final estimation. Okay, so I would take I think that, again, the textbook wants you to take the 2 middle ones. But you could actually use symmetry and find the average of all of them. The average of these 2 is 2. The average of those 2 is 2. They all work out nicely, right? Okay, so we'll show that down here. So I'll say slope of the tangent. That's like a small tan, slope of the tangent equals 2.01 plus 1.99. This is finding the average, which is 2. So therefore, my estimation is 2. Kind of a long process, isn't it? Yep.
Could you just do at that 0.99 and at that 1.01?
Well, so let's be honest. Even if you just did the 1 and you saw that it was close to 2, you'd be like, okay, it's probably 2, right? But it's not. This isn't about it being a useful technique. So no, we're not going to shorten the process. You don't have to do 3 before and 3 after, but you would have to do 2. Okay, that's the deal that I'm going to make. You can do 2 before and 2 after because it's a nice visual that it starts out kind of close to 2 and gets closer to 2. This idea, it's like an asymptote that it's approaching but never quite hitting. Like that's a big idea, folks. So we want to show that before and show it after. So you do at least 2 before, at least 2 after. That's how you would do this process. That would be the minimum that you would be required to do. The textbook for a particular question might ask you to do more or whatever. I don't know. Yes? How did I get this? Is that what you mean? Oh, this here. I added these 2, and I could do it. I added the 2 that were closest, that are also symmetrical, like you want to set it up that way. I added them and divided by 2. I found the average. I found the middle of those 2 points. Does that make sense? Okay, so the second technique is a little bit shorter, and it is called, I'm going to do it down here, it's called centered interval technique. We're going to use the same values, but instead of using the point we're looking for and getting closer, closer, closer. Actually, let me show you something first before we move on to that. Okay, here we go. So here is the preceding and following. So I start at 0.5 and I start at 1, and look at the slope of that line is right there is 1.5, right? We just did that. There it is, 1.5, that guy right there. Does that make sense? Okay, so there it is, and I get closer and closer and closer, and look how it almost already looks like a tangent. You see how that's happening, right? Like now it's just, that's a secant. That's an average between 2 points. As I get closer and closer and closer and closer and closer and closer, and we get so close, and look at that, I get to 0.99, and 1 gives us that same slope as before. So I'm visualizing this process. That's the only thing that I think, that's the one thing that we really want to get out of this estimation process, is that visual, that it's a secant that's getting smaller and smaller and smaller and smaller and smaller. Okay, and then what if I go above? Where was it? Right around there. And put this point right here. And then again, same thing, it's a secant, but I get closer and closer and closer from above, and look how it's approaching. Like you can watch the slope. It's approaching 2, and when I get right on, it's this thing's rounding, so that's why it's getting up, but right onto 2, right? Does that make sense? Okay, so there's our visual for that. So here's the centered. So the centered, we're going to use the same values, but we're going to use the 2 outside, and then the 2 inside, and then the 2 really inside, like the 2 big, the 2 medium, then the 2 small. Okay, so we're centering around. We're not using the actual point. We're centering around. So our first one is going to be 0.5. And this notation of showing what interval you're, like that's an important part. You got to show me what interval it is that you're calculating. Okay. And so that's going to be 3.25 minus 1.25. 1.25 over 1.5 minus 0.5. And what does that work out to? 3.25 minus 1.25 is 2. 1.5 minus 0.5 is 1. 2 divided by 1 is 2. 2? All right? Okay. 1.9 less than or equal to x less than or equal to 2.1. So we're using 2 that are closer. Over 1, what did I do here? 1 point, oh geez, sorry. 0.9 to 1.1, there we go. Okay, so that's right, and then 1.1 minus 0.9, and what does that work out to? I'm going to give you the answer, 2, like exactly, we're not rounding here, it gives you exactly 2. And then 0.99 less than or equal to x less than or equal to 1.01. Okay, so the 2 very insides, and that gives me 2.0201 minus 1.9801 over. Oh my gosh, what does it equal to? So everybody's like, sir, why did we do that other stupid process? This one just gives us the answer. Well, for quadratics, it turns out that if you use that symmetry, it will, but for others, it doesn't as well. And again, this isn't about getting an answer. Okay, I know it's kind of a messy process, but it's not about getting an answer. There's an understanding that's happening here. Okay, so here's the visual, whoops, of this one. I started my 2 points like this, and that's not exact, but I don't know if I'm going to be able to get it right on. There we go. And the slope is 2, and I bring them in closer, but they're still both round, and the slope is 2, and then I bring them in even closer, and I'm not really going to be able to show it, but get really close, and again, the slope is 2, right? So you're starting with, but again, always finding average rates of change. So for this process, you'd have to do 3. For the other process, you'd have to do 4. I'd like to see 3 for this one, so it's kind of up to you, I guess, which one you do. Does that make sense? Any questions about this? Okay, I want you to pick one of the techniques and try it. Notice that this doesn't give me the point. X was 1 in the last one, so I picked values close to 1, below 1, leading up to 1, and then above 1, but close to 1 and leading down towards 1. But this time X is 2. So you're going to pick points similarly, but close to 2. Okay, so try that, and you don't have to do both. You can pick one and do one or the other.